Thank you very much. This is a joint work with Giovanni Gronchi, and I will talk about the linear stability of some periodic orbits in the n-body problem with some special kind of symmetry. So the outline is this one. First, I will introduce and state the problem, and then I will give an algorithm to search for all the periodic orbits we found. And then I will talk about the linear stability of these orbits using numerical methods. So, at the beginning of the 2000s, a lot of periodic orbits of the n-body problem were found using calculus of variation techniques, and some of the authors involved are reported here. And the basic technique is to minimize the action function of the n-body problem on a suitable subset of the T-periodic H1 loops. And the most famous orbit found in this way is the figure-8 orbit of the three-body problem, in which three equal masses chase each other on the same figure-8 shape with a time shift of 1/3. And in general, a choreography of the n-body problem is a periodic solution in which n equal masses follow each other on the same trajectory with a constant time shift. And beside the theoretical work, also a lot of numerical works were done, and in particular, Simon and Kapela were able to prove the linear stability and the Km stability of the figure-8 orbit using rigorous numerical techniques. And the aim of my work was to merge together some of these works in order to apply them to my case study. So now I'm going to introduce the symmetry of the Platonic polyhedra. So we take one of the 5 Platonic polyhedra. It has a rotation group, and we set as n, that is the number of bodies, equal to the order of the rotation group. And then we take n equal masses. So now we have to define the set on which we want to minimize the action function. And to define this set, we impose some constraint on the loops. So the first constraint is a symmetrical constraint that tells that the motion of the other particles is recovered from the motion of one particle, say the first particle, and using the rotations of the group. And this constraint has two important consequences. The first one is that the action functional actually depends only on the generating particle, that is U1. And moreover, the set of the collisions corresponds to the union of the rotation axis of the rotations. So the second constraint that we impose is that the trajectory of the generating particle belongs to a given free homotopy class of the space minus the set of the collisions. And the third constraint is a choreographical constraint, since it says that on the trajectory of the generating particle there are actually m different masses, and they move on this trajectory with a time shift of capital T over n. So now we would like to encode the free homotopy classes, and using the rotation group we can construct an Archimedean polyhedron that has the property that the rotation axis pass through the center of the faces of this polyhedron. So if we want to find a canonical representative of a free homotopy class, we can take a linear piecewise loop that travels on the edges of this Archimedean polyhedron. And moreover, this linear piecewise loop is identified by the touched vertices. So if we number the vertices of the polyhedron, we can represent a free homotopy class using a string, a sequence of integer numbers that represents the vertices. So to state the existence of the minimizers, we have to recover the coercivity of the action functional. And to do this, we only have to ask that the free homotopy class does not wind around one axis only. So at this point, we have a minimizer. And to prove that this is actually a solution of the n-body problem, we have to exclude the collisions. So the partial collisions are excluded, asking some other additional properties on the free homotopy class that can be checked only on the sequence of vertices. And okay, now we have to exclude the total collisions, and the total collisions are excluded using level estimates. So if we suppose that a loop has m total collisions in a period, then we can prove that each section is greater than a constant that can be computed, since it corresponds to the action of an homographic motion, and the values for alpha are reported in this table. And okay, now if we find a loop of the set such that its action is lower than this bound, then the minimizer is collision free. And we can use as a test loop the action, the linear piecewise loop that defines the free homotopy class. So the key point to build up an algorithm to find all these minimizers is that the action of this linear piecewise loop depends only on some constants and on the length of the sequence of vertices. So the relation that excludes the total collisions induces a constraint on the length of the sequence of vertices. And here in this table I reported the maximum length. And moreover, the choreographic condition can be written in terms of the sequence of vertices. And this will help us in the construction of the algorithm. So the idea to find all these free homotopy classes is this one. So we fix the value for m, and we construct all the possible sequences of vertices up to length L over m, and then in some cases we can extend it. And then, of course, we can keep only the good ones. And to construct all these sequences of vertices, we use as basic tool, the adjacency matrix of this Archimedean polyhedron. And here we can see the non-zero elements of this matrix. And this adjacency matrix tells which vertices are connected by a side. So, to sum up, the procedure is this one. So we select an admissible M. We generate all the possible first part of the sequences. Then we check the choreography condition on the first and on the last vertices. And if it is satisfied, we can extend it by symmetry. And if the sequence obtained is periodic, then we can check all the sufficient conditions that ensures the existence of a minimizer on that free homotopy class. So these are the results of this algorithm. In particular, in the case of the tetrahedron, we found 9 different minimizers. In the case of the cube, we found 57 different minimizers. And in the case of the dodecahedron, we found almost 1,500 different periodic orbits. And here, on this website, you can see the complete list of these orbits. And you can see also some videos. So, now we would like to study the linear stability of these orbits. And first, we can state some properties of the monodromy matrix. Indeed, the monodromy matrix is a 6x6 symplectic matrix, and it has a double unitary eigenvalues, one arising from the periodicity and the other one arising from the conservation of the energy. And okay, if we expand the characteristic polynomial of the monodromy matrix, using both the known terms of the expansions that depends only on the entries of the monodromy matrix and the terms that depends only on the other eigenvalues, and here I call the T1 and T2 the sum of reciprocal eigenvalues, we can see that these values T1 and T2 are the roots of a polynomial of degree 2 whose coefficients depend only on the entries of the monodromy matrix. And we can prove also that the eigenvalues of the monodromy matrix lie on the unit circle if and only if they are real, and they are in modulus less than 2. So this has an important consequence from the numerical point of view, since this is an open condition that can be checked numerically, while the belonging to the unit circle cannot be checked numerically. So what we want to do is to find an initial condition for the orbit, integrate the orbit, find an approximation of the monodromy matrix, compute the values of T1 and T2, and check whether these conditions hold or not. So to actually compute these orbits numerically, the first try is to try to minimize the action functional. So we restrict it to the space defined by truncated Fourier series, and now the action functional is defined on a finite dimensional space, and therefore we can apply the gradient descent method. But okay, this method will not work so well when close approaches are present during the motion, since we have to choose a large number of harmonics, and then the gradient descent is very slow to converge. And at the end, we'll obtain a rough approximation for these orbits. But what we can do is to use this rough approximation as a starting point for a Newton method. So we can try to solve this equation that is essentially the choreographic condition. And if we apply the Newton method to this equation, at each step we have to solve a linear system of equations, but in this manner the method will fail, since all the points of the periodic orbits are solution of the previous equation, and near the solution this matrix will be singular. But what we can do is to add an additional transversality condition on the correction, and therefore we ask that the corrections are orthogonal to the vector field. And now we obtain a triangular system of equations that can be solved using the SVD decomposition of the matrix. And of course we can further generalize this method, choosing some intermediate points in the time, and solve a larger system of equations that comprehends also some continuity equations. And this leads to the well-known multiple shooting method that will behave better when close approaches are present along the motion. So these are the differences between the results obtained by the two differences method, and we see that the approximation obtained with the Fourier method and minimize the action is behaves not so well near a close approach, while integrate the equation of motion using a starting point, the result of the shooting method, is better. And okay, no, sorry. Here we can see the complete orbit with 24 bodies, and we can see also the close approaches here, and we can see also that the red curve is a choreographic and the other are obtained rotating.
But no collisions, only close approaches.
Only close approaches, yes, no collisions.
How many points?
These are 24. 24 bodies in the case of the tube, in the case of the Lagrangian, they are 60. Okay? So, if we compute, the monodromy matrix, and we compute also the values for T1 and T2, we see that in all these cases, these are the results, some of the results for the orbits with the cube symmetry. We see that the value of T1 is always greater than 2, and therefore these orbits are almost stable. And our claim is that all the periodic orbits we found with the previous algorithm are unstable, since from the computation we made, the results is that T1 is always greater than 2. But, of course, these are non-rigorous computations. Indeed, to actually have a computer-assisted proof, we have to compute the errors that we make during the integration of the equation of motion and the variational equation. And to do this, we should use a combination of high-order Taylor method to solve the ODEs numerically with a very high precision. We should have to use an arbitrary precision arithmetics, and we also have to use interval arithmetics to obtain a bound for the errors that we make during the computation of the solution with the Taylor method. And once we have the estimation for the errors, we can ensure whether these inequalities hold or not. And I think that's all. Thank you for listening. Yes?
Yes. How do you convert the number of vertices to order?
The number of vertices?
Yes.
No, okay.
The role of transparency with number of vertices, and then almost I can understand. How do you
No, okay, this, maybe you don't understand this relation. Am I right? Further? This one?
here?
Okay.
There are frequencies, and
Yeah.
how is converted to order?
No, okay, because in this proof that I have described here in the first part of the talk, we have some sufficient conditions that the sequence of vertices have to fill to ensure the existence of a minimizer collision free. For example, to ensure the coercivity, we want that the sequence does not win the round one axis one. Okay? So what we want to do is to find all these sequences and check the sufficient conditions that ensure the existence of a minimizer. And the algorithm will do this. We find only the free homotopy classes, that is, the sequence of vertices that satisfies all the properties to ensure the existence of the mass.
And not the orbit itself.
No, not the orbit itself. The orbit is computed numerically.
Okay.
Yes.
I see that you need an order integration.
Yes.
For ordinary differential equation. Are you aware of the format and solve method?
No.
Well, it's excellent. I
Ah.
strongly recommend it. It's a very good documentation. Format is
No, maybe I found that package.
it's around here.
No, yeah,
It's
yeah,
here
so
at the
the
conference.
package. Yes. Yes, I saw that.
Excellent documentation and
Yes.
you can get it from.
Yeah, but I will try. I would like to try to implement that by myself to understand the outputs. But maybe I can use also that. Yeah.
Do you obtain more simple orbit, such as Hip-Hop?
I don't know, but I think no. Only.
Beacon?
Yeah, but because we have this constraint on the number of bodies. That is, if we choose the cube, for example, we have 24 bodies. If we choose the tetrahedron, we have 12 bodies, and if we choose the dodecahedron, we have 60 bodies.
For body and its power.
No, for body itself, yes. But you can find those orbits using maybe among these. Yes.
What determines the number of bodies that you for a given Platonic body? How many bodies? How do you figure out how many bodies?
On the same trajectory. You mean the value of m? Yeah, the value of m is given by the order of the rotations. So the maximal value for m is the maximal value for the orders of the rotation.